Okay, bud. Okay, so this is part 2 of the correlation regression video. I was going to go ahead and show you your homework. So there's an activity correlations for chapter 12. The first thing I ask you to do is enter in the scores, and so you do need to enter in by line. Again, I'm going to show you the output here in case you have challenges with that. So I've entered in all the data. So this was hours studied and this was exam score. Again, this is hypothetical data. I then am going to calculate the correlation coefficient for Pearson by pressing that calculate R. So then you will be taken to this screen. This screen goes over that the R for that data we had is this 0.7786. It then goes through and shows you if you wanted to learn how to report for APA, but I'm not requiring that. It go ahead and gives you a scatter plot of our data. And so again, this is each dot represents one person's score from our data. It then goes through and does the calculations that you would have learned to have done if we would have learned about the R formula, which you can read more about in chapter 12. It does go ahead and give you the means. So the mean for hours studied was 6.636. The mean for the exam score was 68.409. And so that is your means. I do ask you about those means. And then it gives you the coefficient of determination, which is R squared, which is 0.6062. Again, that was taking our R and squaring it. So then I'm going to go ahead and go back, and I ask you to do one more thing with the data. So I go back and I ask you, and I told you to take that last score from 100 and make it 10 and calculate the R, so that you would have done that. Now, oh my goodness, just changing one score, we have an R, a new R. So that new calculated R is 0.1289. Again, it shows you the data. Again, now you can see we have this outlier. I talked a little bit about outliers in the first video. Outliers are not good. They really can dramatically change your R scores for better or for worse. You can see that the mean didn't change for our study because we didn't do that number. The mean changed slightly for our Y values, changing that one score. Again, we changed one score out of those, but although the mean doesn't change dramatically, the R does. And again, changing the R also changes that coefficient. So the new coefficient is 0.0166, so 1.66% of the variance is shared for exam scores. And this is a case with this homework you could say our study predicts exam scores, which leads us into our part 2 of our lecture. So our part 2 of our lecture looks at the taking a correlation and then moving it to a prediction, which is a regression. So when we're talking about a regression, we are wanting to make a prediction. Our prediction is going to be our X variable. So in the homework example, hours studied is predicting, and that's an variable, which we need, is predicting my test score, my outcome variable, which is my Y. When we're going through and doing this, it's important to note the terminology here. So the terminology, what we once called X as the independent variable, we can now call it as the predictor. We're now going to call the outcome variable, instead of calling it dependent, which is used more in terminology for an experimental design, we are going to refer to it as a criterion. So outcome is criterion. So your book had hours of sleep and mood as an example. So hours of sleep would predict my mood. My mood is coming after my hours of sleep. So we've got that time factor kind of giving us a reason to run a regression. A regression is a take on a correlation. And so a correlation, you're interested in relationships. So here I've got some fake data with coffee consumption and happiness. All these dots refer to each person's score for how many cups of coffee they drank and how happy they were, asking them about their happiness. So for these, you can see I have a positive correlation. The line you see in this photo or image is a regression line. A regression line is meant to predict something. So based on your coffee consumption, can I predict how happy you are? Based on your hours studied, can I predict your exam score? Based on measurements of a fetus, can I predict a birth date, a due date? Again, that would be something with a multiple regression. I take multiple measurements of the fetus, and then from those measurements, I would determine what the estimated due date was. So when we're going through and doing this, again, it's take one step up from a correlation. I first need to identify there is a relationship between these two variables. I need to identify that indeed one can predict the other. So that could be in terms of time point 1, I collect this variable, time point 2, I collect that variable. It could be connected as well to your research design. When we're going through, again, making those predictions, it's really helpful for us. Again, in the case of a stats class, I haven't actually taken all your data and ever done this, but I could go through and say, what is the best predictor of your grade? And so then I would kind of be looking at that. Superficially, I could say a mean grade for your stats class would be something that I would be interested in taking into account, but I also might want to look at some other things that are making predictions. I also need to identify how much variance is going on in my sample. The more variance I have, the more volatile it will be and the harder it will be for me to predict. And we've seen this challenge of more variation leads to messiness in statistics this whole entire semester. And I'll talk more about that in your wrap-up video next week. So it is great and useful in looking at data, and it goes beyond our descriptive statistics. When we do a regression, this is the formula for your regression line. So this is when you have a raw score. This is when you have a z-score. And I'm not going to talk too much about the regression formula because I'm not going to have us do too much with it, other than y hat is your predicted outcome score, your predicted criterion. A is your intercept. B or beta, depending on if you're using standardized data, which would be z-scores. You know z-scores. Z-scores are standardized data. Or raw scores would be connected to the relationship that's going on between those two things. So again, some terminology. B would be a raw score regression coefficient, in a standardized when I'm calculating this with z-scores. Your beta is basically your R. It's how related they are in that the relationship between the criterion and the outcome. And then A is your constant. A is where the number that's going to fall on your axis when x is 0, your y-axis when x is 0. So I want you to take a look at these three different samples. So these three different samples, if you look at this, they all have the same regression equation. Can you believe it? So again, our A, where we're seeing it hit the y-axis is that 61.2. So when x is 0 in this made-up data, 61.2 is the y-intercept. That's A in a regression line. Looking at our B, so again, this isn't standardized data. Our B is negative 0.85. That negative makes sense for all this data. All of these data, you have a negative relationship there. Again, in this example, we're looking at unstandardized regression equation. And then why is my outcome? So these are all the same. How can that be? All of this data is different. Well, all of this data is trying to get at a regression line. A regression line is the best fit line. It is trying to minimize the gap between your predicted line, which is that red line, and your data sets. So of these three, although they have the same regression line, they're going to have a different significance level. They're going to have a different report of error that's going on there. Again, which one do you think has the least amount of error? Which one has less gaps between those dots? That would be the one with the least amount of error. That would be the strongest predictor. The one that has the greatest gaps would be our weakest regression line and would be our weakest predictor. And again, we still could look at p-values to determine significance. All right, so all of these, this one is my strongest equation, and I can tell that too because if I actually looked at this, this would be a correlation of -1. All right, this might be a correlation of 0.8 something, and this might be more like 0.4, maybe 0.5. Again, I still can see a linear trend with all of these. So when we look at regressions, part of the things that are going to determine significance is something called the principles of least squares. Again, that's trying to minimize the dots. You're trying to minimize the gaps between my actual scores and my predictor. All right, so each one has that gap. The standard error of the estimate, all that is going to take an average of all the gaps and give you an error estimate. And we're actually not going to focus too much on that, but that's something that's used in creating this equation. And then obviously with R squared, that's still going to give you an understanding of how strong the relationship is. And that still is R times R. All right, so I wanted to go ahead and have you know, before I go into a little bit of a simulation, multiple regression, all you're doing is taking more predictors. So the example of a due date for a fetus would be using multiple predictors, measuring the different parts of the fetus, and then using all that data to get a predictor when that due date would be. When you go through and run a regression, you still have to worry about things like your measures being independent of each other. So some other things that you should know, I'm going to do this simulation in a minute, but I talked about multiple regression being more than one predictor. So the example of the due date, you take multiple measures of the fetus and then use that to predict the due date. We still have some assumptions for regression, and you wouldn't want to run a regression if the correlation was curvilinear. Again, it's just for a linear relationship, just like the Pearson correlation. Again, we wouldn't want to do that if we were just focused on one aspect or one subset of the data. That's that restriction of range issue. And so those were some other things to consider. And then you've got key points. So the last couple of minutes, I wanted to go ahead and rerun this simulation. And so again, when interpreting a regression, it's useful to consider looking at the B, which is interpreting the relationship, and then the A is the intercept. So in this, looking at does weight loss predict self-esteem, you'd see there is a relationship between weight loss and self-esteem with that 0.5. And then if you had no weight loss, then the interpretation of that y-intercept would be your self-esteem would be a score of 5. If we had a case where, so again, that's pointing that out. And in another example, if I had a case and it looks something like this for weight loss, again, my regression line is going to be a little bit different, and it's going to indicate there's really not much of a relationship going on there. Again, that B is 0.03. If I had lost no weight, then my self-esteem would be a score of 4 on that. Again, the intercept for the y-intercept, that A, is not always meaningful, but in some contexts it does make sense to interpret that. Again, that intercept is always interpreting when x equals 0. The slope can be interpreted for amount of change in your outcome variable for every unit of your x. So in the same example with self-esteem and weight loss, 0.5 x plus 5 means that for every pound you lose, you gain a half a point of self-esteem. And so again, there's some interpretation that can be done when you're looking at that slope. So I hope this part 2 of the video is helpful for you in better understanding the regression. And again, that first part of part 2 assists you with completing the activity for the homework. All right, thanks.